Hello, I'm Dr. Jacob Hudis. Welcome to this video where I'll explain what center of mass is, as well as solve 5 carefully chosen problems to help you understand the concepts. The last 2 problems involve integral calculus. This is video 7 in my rotational motion playlist. First of all, what is the center of mass? The center of mass is the point where all of an object's mass can be thought of as being concentrated for the purposes of analyzing motion. These are the formulas for the x, y, and z positions of the center of mass. The position of the x center of mass is given by 1 over the total mass of the object times the sum of the constituent masses multiplied by the distance from the rotation axis. These formulas are much easier to understand with an example, and that will be coming shortly. Here's an animation of an object being projected through the air. I'm going to hit pause. This path here is the motion of the center of mass. As you can see, the motion of any object can always be broken up into the translation of the center of mass and the rotation about the center of mass. For objects with sufficient symmetry, the center of mass lies at a point where the symmetry lines intersect. Below are 3 examples in 2 dimensions. Here's a circle. I can draw a vertical line directly through the center of the circle, and that divides the circle into 2 symmetric halves. I can draw a horizontal line directly through the center of the circle, and that divides the circle into 2 symmetric halves. The location where those 2 lines intersect is the center of mass of the object. Terrific. And it's the same for a square. Here's a triangle, and I can draw a vertical symmetry line through the triangle. I can also draw these diagonal symmetry lines through the triangle. The line of symmetry BE cuts the triangle into 2 equal halves. The location where the lines of symmetry meet is the center of mass of the object. For this object, I can draw a vertical line and divide it symmetrically in half. I know that this is the location of the x center of mass, but I can't find the y center of mass using symmetry. This object is not symmetric in the y direction. Here's an example that asks us to find the center of mass of the Earth-Sun system. To begin, we have to define an origin of the coordinate system. You can put it anywhere. I'm going to define the origin is going to be at the center of the sun. The center of mass is equal to mass 1 times the position of mass 1 from the origin, plus mass 2 times the position of mass 2 from the origin divided by the total mass of the system. Mass 1 is the mass of the sun, and it's at a distance of 0 from the origin. And mass 2 is the mass of the Earth, a distance of 1.5 times 10 to the 11th meters from the center of the sun. So this is where the center of mass is located. It's heavily shifted towards the sun because the sun is so much more massive than the Earth is. The next question says, what is the center of mass of this triangle with 3 different masses? I'll call this location the origin. Mass 1 is 3 kilograms located at negative 2, 0. Mass 2 is 2 kilograms at 2, 0. And mass 3 is 1 kilograms at 0, 2. To find the x position of the center of mass, you take mass 1, 3 kilograms, and multiply it by its x position of negative 2. And then I add that to mass 2 of 2 kilograms and multiply it by 2. And I add that to mass 3, which is 1 kilogram at an x location of 0. You then divide by the total mass of 6, and the x position of the center of mass is negative 1/3. The y position of the center of mass is calculated the same way. Mass 1 times its y position, plus mass 2 times its y position, plus mass 3 times its y position of 2, divided by the total mass, and that gives you 1/3. This x is the location of the center of mass of this triangle. Problem number 3 asks us to find the center of mass of this aluminum object shaped like a U. The position of the y center of mass is given by 1 over m times the sum of yi mi. Y sub I is the y position of each one of these individual metal square plates, and m sub I is the mass of each individual plate. Mass is equal to sigma times A, where sigma is mass per area. I can replace this little m with sigma AI, and I can replace the big M with the sum of all the little m's. The sigma cancels on top and bottom. For an object like this, we can calculate the center of mass using this formula, the sum of yiai over the total area of the object. I'll show you how it works on the next slide. Each one of these squares is 20 by 20, so the area of an individual plate is 400 centimeters squared, and the total area of the object is 6 times 400, or 2400 centimeters squared. To find the x position of the center of mass, I take 1 over the total area, and I multiply A1 times its x position, which is 10, plus A2, which is 400, times its x position, which is 30, plus A3, they all have the same area, times its x position of 50, plus A4 times its x position of 10, plus A5 times its x position of 10, plus A6 times its x position of 30, and that gives me an x center of mass of 23.3 centimeters. I can use the same formula to calculate the y center of mass, and that's 26.6 centimeters. This x is the location of the center of mass for this object. Notice the center of mass is not actually on the object. It's not uncommon for the center of mass to be located off of the object. Problems 4 and 5 involve integral calculus.
AcePhysics.org. Math and physics tutoring with Dr. Hudis.
Here's problem number 4. Find the center of mass of this solid cone of height h and base r. This is a 3D picture of the cylindrical cone, and here's a cross section. The total height of the cone is big H, and the radius of the cone is big R. Any location along this axis is given by z, unless you're all the way at the top, in which case it's big H. At this location, we'll call the radius little r. This allows us to write down a ratio because we have similar triangles. Big R over big H equals little r over little h, where little h is z. The formula to compute the z location of the center of mass is 1 over m times the integral of z dm. Let's discuss what this integral is doing. The integral takes the mass of this small cylindrical plate multiplied by its z distance from the ground, and then adds it to the mass of the next cylinder multiplied by its z distance from the ground, and it continues that sum for the entire object. The cylindrical plate at top has the largest radius, and therefore it has the largest volume and the largest mass. The tiny little cylinder at the bottom has the smallest radius and the smallest mass. That's how this formula calculates the z component of the center of mass. The mass of each cylindrical plate is equal to the mass density times the volume of the plate. The volume of each plate is equal to the area times a small height dz. Area is pi r squared. But we know from this ratio that r is equal to big RZ over h. That gives us this formula for dv. I can plug this in for dv, and then we're left with this expression. It's a simple integral that only involves z. The algebra is relatively straightforward. It's all worked out on this slide, and the end result is the position of the z center of mass is equal to 3/4 of the height of the cone. That location follows the sanity check that roughly half the mass will be above it and half the mass will be below it. And here's the fifth and final problem. A uniform rod of length 40 centimeters has a linear mass density described by the expression lambda equals 10 theta squared, and the units are kilograms per meter. Theta is measured relative to the x-axis. This tells us that this rod's density changes as a function of theta. It's most dense up here, and the density decreases as theta decreases to 0. Question A, what is the total mass of the rod? And B, what are the x and y coordinates of the center of mass of the rod? Mass is equal to the integral of the linear mass density times ds, where ds is a small distance along the edge of this rod. ds is equal to r d theta. The integral can be written like this. I know the arc length of this is equal to r times theta, where theta is pi over 2. This allows us to solve for the radius, 0.8 over pi. When you plug everything into the integral and pull out the constants, you get a simple expression. Performing the integral tells us the mass of this rod is 100 pi squared over 3 kilograms. Part B asks us to calculate the center of mass of this object. To do that, we break this object up into many small mass elements. The x position of the center of mass is equal to 1 over the mass of the rod times the integral of x dm. X represents the x position of a specific mass element. X equals r cosine of theta, dm equals lambda ds, and that results in this expression for the x center of mass. The y center of mass works exactly the same way, with the one difference that the y location of the mass element is given by r sine of theta. Putting all that together gives this expression for the y center of mass of the object. You can use a computer to help you calculate these integrals. Substituting the values for radius and for mass gives the final result for the x and y position of the center of mass of this object.
AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.